All right. Anything else from the quiz or from homework or anything? Okay. All right. If there's nothing, we're just gonna keep going. So let's see. Last time, I think I'm pretty sure I unlocked the polar graph in Canvas. I have blank polar graph paper up in Canvas. So you could do that one section with plotting polar points, right? Did we finish that handout with the polar stuff? I'm pretty sure we did. I don't know if I have one with me. No. No. Okay. So there's that handout. Yeah, on one side it's got all the shapes that you could make with polar coordinates. And on the other side it's got the polar graph paper at the bottom. Right? We finished that, didn't we? Yeah, we did. Okay. So a few people had questions earlier from the homework. You just got to get in there and try them out. So, for example, if I saw this, sure. So just remind me, guys, what was this again? What shape is this?
A circle.
Circle with radius
1.
1. What's this?
That's a
Circle with radius
4.
Nope. X squared plus y squared equals r.
Well, that's a y, or that was a 4?
X squared plus y squared equals r squared. So what's the radius if x squared plus y squared equals 4? What's the radius?
Oh, like a 4.
No, x squared plus y squared equals r squared. So if x squared plus y squared equals 4, r is 2. Yes. So do you see how this is a circle, a radius 2, that's been shifted? Which way would this shift it?
To the left.
To the left 2. So we know this shit. We know this, right? I want to convert this to polar coordinates. So the formula in polar coordinates should be much simpler because polar is all about freaking circles. So how do I do that? There's 2 ways I could do that. What all do we know? So I already gave us one thing. X squared plus y squared equals r squared. We know that's true. What's x?
R times
R
cosine.
cosine.
R cosine theta. And what helps you with that? Does SOHCAHTOA help you with that shit? No. X likes cosine helps you with that. Y equals r
Sine theta.
sine theta. Holy shit. Right? And we know some other stuff, but it doesn't matter for us right now. I could. So there's problems just like this in the homework. We just did one earlier, actually. I could replace x and y right now with these. But then I have to do algebra with these. I'd rather not. I'd rather simplify that thing now. How do I simplify that expression?
Is that x minus 12? Is that what it is? Okay. Oh, plus 2. Oh, that's different.
How do I simplify this? What's the only thing you can do in here?
Well, you foil the x plus
Yeah, that's the only thing I can do, yeah. So if I FOIL that, I'll get what? X squared,
X squared.
2x and 2x,
2x.
2 times 2,
Right.
4.
2 is 4, yeah.
Now, do you see anything that goes directly into polar really nice in what I just wrote? Is there anything that goes right into polar?
2 and 1.
X squared plus y squared, what's that?
R
1.
R
squared.
squared. And what's x in polar?
R cosine theta.
And what happens to the 4s?
Well, they cancel, they kill each other.
Yep. Okay, let me stop for a minute. Any algebraic simplification you could do it first. Because you might get some like x squared plus y squared, which kicks so much ass. Because I can replace both of those with r squared. That's awesome. What's one last thing I could do here?
You could divide by R.
Divide by r. This is fine, or you can say that this equals r equals -4 cosine theta. Okay, now, you guys sort of with me? Okay. So if I'm doing this homework and I don't have sitting next to me either these written down or that worksheet with these written down, I'm a strange person. I should have this stuff sitting next to me because as I'm doing the homework, I'm getting used to them. When I get to the test, I gotta know them. But while I'm doing the homework, I'm getting used to them, right? So it's not a bad idea to do the homework and go, I think it's this, and then double check and go, okay, that's right, or oh shit, I was wrong, just to kind of keep getting it into your brain, right? So remind me again, this is a circle of radius 2 that was shifted where? To the left 2. Is everybody with that? Because x plus 2 inside, of course, makes it go back 2. Are you with me? Okay. Don't have the grades? Okay, thank God. So this is a circle of radius 2. Wow! Look how nice that formula is. Of course it is, because the polar coordinates are based on circles. So of course it should be quick to make a circle. Now if I put in there -4 cosine theta, how did that circle move? Let me put them both up there. That'd be smart, Jeff.
-2 to the left.
Which is what we knew it would do. Now, so this is not surprising. This is not amazing, but it is nifty to see what we know should happen actually happen, even if we're in polar or something weird. You guys semi with me? Quiet. So if I change this, then I can see how that's neat. That would be shifting it over that way. Let's start back. Looks like a frog. Exactly. All right, anything from homework now? Any other stuff? Let me catch up with some of you guys. What's up? Oh, sure. I think that's everybody. All right, guys. So let's do this. If there's no other questions about polar stuff, and I hope at least one of you guys, I think somebody already did this. I think Mike, you were saying you did this. Jump into Desmos and just play around with this shit because you can get some really nifty stuff happening. Just if I come back to here, and I put in here 2, it's just so nifty how you have to do very little and some really cool stuff happens. Okay. Somebody got serious. All right. So let's do this. So last time I introduced the idea of parametric equations. This is section 10.6, 10.7. 10.6 is about parametric equations, 10.7 is about graphing those. I really wish they just made that one section. It's kind of silly, but too bad for us. So let me let's do this. If I give you a system of parametric equations, okay. Now, how would I graph this by hand? What would I have to do? Or what should you do?
Make a table,
What kind of table?
the three,
Good. The T, X, Y. No, you're my one pen I have left. Damn it. All right, I'm gonna go to. No, you're dead. All right, pencil. Sure. Let's see if that even shows up. Oh, let's see if this works. Yeah, that works. I'm okay. Thank you, though. So I have to tell you that T lives between, let's say it lives between -1 and 1, right? So this part should just be, you can just eat this up. Because you know how to make tables. It's just the one thing that's tricky is I'm not picking a value for X or Y, I'm picking a value for T. Because T controls everything. T is behind the scenes. T is the Illuminati. Why not? I'm joking, everybody.
Illuminati?
Illuminati, yes. If you don't know who the Illuminati is, I feel pretty good. That's a good thing. Don't look them up, kids. So if I plug in here -1 and a 1, I'm going to leave some. Well, I should plug in 0 at least. What do I get when I put a -1 in?
1.
1 plus 3?
Oh, plus 3.
three, one plus four.
And then when I put a -1 in here, I get
Negative two.
-2. When I put a 0 in,
Three.
3. When I put a 0 in,
Zero.
when I put a 1 in, sorry, here, 4. And when I put a when I put a 1 in here, 2. Crazy sauce. And so if I want to graph this, I always do this for myself to remind me that these are the points, this is the behind the scenes. This is the person turning the knobs on the Etch-a-Sketch.
Oh.
So when I go to plot this, let's see. You need to go up to 4, and it needs to go up and down to 2 at least. Okay. So it'll be 4, -2, 3, 0, 4, 2. Jeff, you can do it, buddy. You set yourself up. You went 1 too much. So it looks like this. Now let me ask you this. I start at 4, -2, correct? That's the first point I did? And then I went to 3, 0, and then I went to there. So one extra thing you could do is show the direction of motion.
Oh.
So now you start to see why I would use parametric equations to define where a missile is or where a comet is or something. Because not only does it give me the shape of the motion, it actually gives me the direction it's moving in. Okay, I like it. Hey, Mikey. Now, if you have a function that's like bouncing all over the place, and I should have made a more funky one, but I think I do have one. You might have to put more points in the middle just to get more resolution. You might have to plug a -1/2 in or a 1/2. Just for fun, let's put a 1/2 in. What do I get when I put a 1/2 in? 1/2 squared. 1/4 plus 3, so it'd be 3.25. Is that cool? And then 1/2 times 2 is, holy shit. So if I go 3.25, 1, that's about right there roughly, so I'm on this. I didn't need it. But you might get some problems where if you just do whole numbers, you don't know it's bouncing too much. So you might have to put something in the middle to see, is it curving this way, is it curving that way? We'll see an example. I got a worksheet, believe it or not.
A worksheet, you never have those.
I know, it's weird. I'm trying something new. Let me ask you this. Is everybody semi-cool with this? Please let this must be nice. You have to let this be nice. Because you could also check, how would I check this? Put it in the damn calculator. You got the parametric mode we talked about, right? So let's see. Here's one extra thing. I don't remember if I told you about the calculator with this. Let me make sure I'm in parametric. So there's parametric there. If you put it into parametric mode and you hit y equals, you get this business. So if I put in there t, there's your all-purpose variable button. T squared,
Wait, so how do I put the T in?
there's your all-purpose t variable button right there, next to alpha.
Oh, it's just how you would put X in, okay.
Yep. Depending on what mode you're in, it does the right variable.
Oh, okay.
So for
got it.
polar, it's got a theta, and N is for something called sequential, which we might talk about at the end of the, I don't know if we're gonna have time. And then I put 2t in for y. Now one little thing you gotta be careful about, where's t supposed to go from? Negative 1 to 1. So I got a window, and it can define t to go from negative 1 to 1. Don't worry about all this other shit. Let me see, what's my graph go? Let's do this. My graph goes from negative 3 to 3. Is that cool? I'm going to make it more like my graph. So from negative 3, Jeff, you could do it, buddy. Negative 3 to 3. And the x for me goes from like negative 1 to 4, let's say. There we go. So I'm going to try to mimic this. Hey, it's not too bad.
Yeah, it's kind of deformed because of the shape of the display.
Yes. What's got me a little concerned, let me make sure I put this in here right. T squared plus 3, 2t. Yeah. That's a little weird that it doesn't go through.
I'm not even getting that shape. I just got a straight line.
What's that say? Oh, it does say 3, 0. Okay, good.
You got a straight line?
Yeah.
So, let me see. You did this.
Yes.
Okay. Bless you.
Sorry for the transparent one.
Oh,
That was weird.
okay. It's like when you call a repairman and that's the only time the thing works.
Yep.
You guys all with me? See, so it's relative. I know you know how to make XY tables. Now it's just a TXY table. No big deal. You can plot points. I know you can plot points. And you can check your work using, well, unless you accidentally hit a button and kill your T, but oh well, too bad. So, one more thing I want to talk about with this problem. Let me rewrite this problem down here. I want to get rid of T. Right? The British are going to rebel, but I want to get rid of T. How do I kill T between these two equations? How do we get rid of T? We know how to do this.
Subtract.
Look at the second equation. Can you solve it for T?
Design.
Yep. So what do we know T is from the second equation? T is,
Is equal to.
we know that's true, don't we? Because that's something they gave us, so I know this is true. Is everybody with me?
Yeah?
If that's true, which they told us it is, then this must be true. So can't I plug this there? Because that's a frickin' T.
Yeah.
Anybody know what this process is called?
Substitution?
Substitution, yeah. Stop looking at the screen, Jeff. So I get that.
Yay!
So very quickly, guys. Doesn't this, if I kept going, this would look, what would this look like?
A parabola.
Parabola that's fallen over, correct? Y equals x squared looks like this. X equals y squared looks like that. And what do we get? X equals stuff with y squared, correct? It's just been shifted a little bit. So that makes sense. So there's two things I'm going to ask you to do with parametric equations. I'm going to ask you to graph them. I'm going to ask you to kill the t. It's actually called eliminate the parameter. Exterminate. So let me give you this. want you guys to work on this. You can work with other people, work by yourself. Four, yeah, sorry. Yeah, line four. Alright, so give that a try. Of course, you know, I give you that equation. So guys, if you plug a -3 in, the angle's -3 pi over 2, right? Where's that? -3 pi over 2. It's there. So what's the sine of that? What's the sine of that? Yep. 1. Good. 1 times 4. Let me go back in time for a second. I'm a little concerned about me. What's the sine of 2 pi?
1.
I think I just took what somebody said and went with it. 0. Okay. And this will be 4.
Oh, the sign of.
Sine of 2 pi. What do I get here when I put in -3 in?
I was thinking of pi over 2.
I'm with you. When I put a -3 in here, you should be able to do this without a calculator.
-3.
-3 squared is
9.
9. Cut in half is
4.5.
-4 is
1/2.
1/2. Right? You don't need those stinking calculators. You can
We
do it.
don't need no stinking calculator.
There it is. You guys all with me? I will show you, well, I'll show you something kind of cool in a minute after I force you to go through this. So what do you guys get when you put in -2 in? -2 divided by 2 is -1. What's the sign of negative pi? 0. And then when you plug -2 in there, it's going to be nice. -2 squared is 4 divided by 2 is 2 minus 4 is -2. Okay. Right? This isn't that bad. Say again? No, that's cosine. Cosine and negative pi is -1.
Oh my god.
Yeah. So if we're on the x-axis, don't worry, I did the same thing earlier. If we're on the x-axis, the sine doesn't like it there because it's all x.
Oh wow. I was thinking okay.
You're okay.
Oh, geez,
What's up?
okay, so I'll look like -2. Okay, okay.
Are you trying to think about the graph's going to be?
No, I'm looking at the x. Okay, so I got like -2
Over 2.
over 2 is
Is-
-1.
Yep, so the sine in negative pi is on the x-axis, sine likes y, so that's 0.
Okay,
Yep, okay. -1, you get negative pi over 2, right?
right.
Where's negative pi over 2?
It's gonna be, where 3 pi over 2 is.
Good. And what's the sign there?
Uh,
-1, good. Times 4 is -4. If I put a -1 in here, -1 squared is
you
1
think
times
so
1
much
half.
faster than I do.
That's okay.
No, it ain't.
-1 squared,
Makes me crazy.
1 times 1 half is 1 half. 1 half minus 4.
Half minus 4.
What's 4 minus a half? Then you just make it negative, right? -3.5. So if I have to do 1/2 minus 4, I could do the negative of 4 minus 1/2. Our brain latches onto that better, so of course we let our brain latch on. How are we doing so far? Okay. But put a 0 in. Sign of 0 is 0. Do you guys see the pattern? Right? Sign's all about patterns. So screw sign now. So what's sign going to do next? What's the pattern here? Let's fill this in. What's it going to do next?
4,
4, then,
negative 4,
then.
0.
Ah, yeah, we got you, sign. We made you. Raw. All right, we're the freaking humans here. We know some shit. It's always going to be some multiple of pi over 2, so I'm going to keep on getting the same answers. Once I see what they are, I can just finish it out. I don't have to do every damn step. Now this one is not periodic, you bastard. But it is repetitive, because a parabola will repeat outputs, won't it? So when I put a 0 in, what do I get?
One half of 0.
I'll get 0 minus 4. I get negative 4. Then when I put a 1 in, aren't I going to get the same thing as negative 1? Because the square is going to make it. So then I just repeat this shit going this way. So negative 3.5, negative 2.5, 4. Do you understand? When I give you trig, when I give you parabolas, they repeat at some point. Parabolas have a midpoint and they repeat around it. And of course, sine and cosine, they just sort of like constantly repeat forever.
Because they're even.
Not just that. I mean, sine's not even.
No, but a parabola's even.
Even parabola's even, but it is more because it's going to repeat the same outputs even if I move it over and make it not even anymore. It's going to still repeat the same outputs. Yeah.
Oh, that's true.
Yep. So let's try to plot this. So here's what I do visually just to make sure my eyeballs go in the right place. Stay with me now. What kind of scale should I make? Does 5 to 5 work? Negative 5 to 5, negative 5 to 5? Does it work? Yeah, because there's no x's or y's bigger than negative 5 or 5, right? More further away. So we're just going to use the negative 5 to 5. So 0, 4. Go ahead and try to plot that. Be very careful. I want you to track the motion. I want you to put arrows on. As you plot these, you can connect them and put arrows. Let's see what shape we get. You guys with me so far? You see that? Huh? You have the same points though, right? I know it's going to be a little curvy because it comes from a squared and a side, so there should be a curve to it. It shouldn't be straight lines. So I kind of make a little curve to it. If I really want to know how the curve is really going, maybe it goes way out here, I don't know. I have to do another point in the middle. But I don't think I need it. Somebody with me down here? So I plotted that point, I plotted the next point, I connect them with a bit of a curved line, not a straight line. Put an arrow. Plot the next point, connect them. Put an arrow. This looks more parabolic, less curvy. It also looks sine, doesn't it? So that's, I know that it's comprised of those two, so it should be curvy, not straight. Next point, curvy, arrow. Next point, curvy, arrow. And then I start to repeat some stuff. 4, negative 3.5, 0, -2 again, -4, 0.5, and then 0, 4, and back to here. Now come on, that's a neat shape, come on. What shape is that? Anybody? What do you guys see? It's like looking at the clouds. Goldfish, I love it. Goldfish kind of like
So
coming.
lotus.
It's like the giant goldfish, like Jaws. Somebody's swimming, there's this big goldfish coming up. Or, what?
We wrote this in Brussels.
What?
It's like a half lotus position.
Oh, okay. Got you. Lotus blossom. That's what you said. I didn't know what you said. I thought you said some German guy. Looks like a spade, looks like a, yeah, you can see how much it looks like. It looks like a Goopa from Mario Brothers. Fish, okay, everybody's going fish, okay. And then, of course, if I go here, let me do it with a calculator, actually. So if I put into my calculator, put in here, let's see, 4 sine pi t divided by 2. I did e again, didn't I? Let me make sure I am in radians. So just 4 sine pi t over 2, and then I can put in here 1/2. You can do it, Jeff. No, you can't. There it is. 1/2 t squared minus 4. Right? You can just plot them on in the parametric. Let me make sure my window's right. I need t to go from -4 to 4. And just to make it look more like my graph, I'm going to make my x-min go from -5 to 5, and my y to go from -5 to 5. Now it should look more like my graph, right? If I match up the scale. Hit graph. Chabow! Look at that. Yeah. That looks nice. Just to show you real quick, there's a little thing called t-step. If I make it big, 0.5, watch this. Janky. It's really the resolution. So it's kind of like the step between what it plots. So if I make it 1, it assumes straight lines. If it would have just been curvy like we did, it would have been a little bit better. But if I give it more resolution, if I make t-step 0.1, that's better. If I make t-step, you can do it, Jeff, 0.01. Yeah, now it's going to take its time. That's kind of nice. I like to ramp that up because then you can watch it create. It's kind of nifty. Zaba. How you guys doing?
Ace of spades.
So there is the y, in the y direction, just the y direction. What shape would it have if I plotted a ty? What's the y formula? What's the y function?
Arc close.
No. What's the y function for this parametric system of equations?
Y
T.
equals 1/2 t squared.
So it's a parabola, correct? So, do you see how when it started, the y was 4, then the y goes to -4. Don't the outputs, they started at 4. Let me graph this again. Watch this. Make this even. There. You ready? Y output starts at 4, goes down to -4, then it turns back around and comes back up. So, what that means is, the outputs are going like a parabola, right? The outputs are going from -4, they went down, 4, they went down to -4, then they went back up to 4. So if I gave it more room, this should actually grow up, because the y output should be able to go like a parabola. It should be able to go up to infinity. So let's see, if I do this, if I make t min and max, let's say go from -10 to 10, I'm also going to have to step out a bit. You guys don't have to be able to do this yourself, but let me just show you. Maybe nothing will happen. There it is. I didn't go up high enough. Yeah, that's cool. I should have probably let it go a little faster. It'll just keep doing this forever. So can you guys see in the y direction the outputs come down and go back up, just like a parabola? What's happening in the x direction? Wow, 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 like that, right? And of course, what's the x formula? What's the x equation?
4,
It's a sine. So of course it's going to look like a sine. It's going to go back and forth in the x. And the y, it's going to go down and then back up. And maybe. So it's just going to keep doing this forever. The little, what would you call those? The little bumpy parts just get bigger and bigger and bigger as it goes up. Okay. All right. So just to cut to the chase here a bit. Somebody with me? That's kind of cool. You got to admit that's a little cool.
T squared, you're gonna get a.
In the y direction,
You're gonna get a quadratic because of the square.
you're going to get a parabola, yeah. So in the y direction, it started up here, it came down to -4 and then went back up. So it made a parabola. So the y outputs went from 4 to -4 back to 4 on our picture. While the x bounced between 4 and -4 because the biggest sine output is 1 and the smallest is -1. So of course the x goes between 4 and -. So if I made that a 5, what would happen to this? If I made that a 5, the x's could now go from, no, if I made it a 5, the x's could now go from -5 to 5, it would just get wider.
I see.
Okay. I like it. And one little thing you can do in Desmos, by the way, that's not easy to do on your calculator. I gotta remember how to do this now. Parametric in Desmos is a little weird. Let me see if I remember how to do it. Get in there. That's x and y was. That's not true. I gotta remember how to do this, darn it. You have to put it in. Oh, I see what I did. There it is. Okay. And of course, t goes from -4 to 4. Yes? That's nice. So I could very easily make t go from -14 to 14. It's just easier to play around. And if I make this a, I can then add a slider, and then I can see it gets wider. It inverts if I do that. You guys with me? If I make a 0, I get this very boring.
Gnarly, man.
Yeah, totally. Okay, sorry. You can even add another slider if you want to. You can leave your friends behind. Look at that. What's that? This is really weird to talk about, but that just, the B kind of tells me how quickly the Y outputs are changing. The slope of the parabola. So it's going up really fast, or it's not going up very fast at all. It gets really squat, and then I can smoosh it all the way down, smoosh it all the way down, smoosh, and then it goes the other way.
It's leaky, it's leaky.
Okay, stop. Okay. It's log. It's fun for a girl. All right, so real quick, this one, yeah, let's do this together real quick. -1 to 3. Let me show you how you should do these in general. Okay, here's how you should really do these. -1, leave some room. 0, leave some room. 1, leave some room. 2, leave some room. 3. Leave some room just in case the points are going insane and you're like, I don't know. You have to give yourself more information, right? So let's do this together. When I put a -1 in, I get -1 minus 3 times 1. I get -1 minus 3, -4. Here on this one, I'll show you the ultimate shortcut on your calculator. When I plug a -1 here, I get -2 minus 3 is -5. That's crazy. When I plug 0 in, I get 0. Over here, I get -3. When I plug a 1 in, I get 1 minus 3. And do you guys notice this is a linear equation, slope 2? So I just keep adding 2. See, kids, it's good to know shit. So I don't have to do all that work. I just know it's going to go up by 2 because that's the frickin' slope. Yes? So these are just going to go up by 2. When I plug a 2 in,
You get negative 4.
you get 8 minus 3 times 4. So you get 8 minus 12, negative 4. Just want to catch up to Brooke. And then 3, I'll get 27 minus 3 times 9. I get 27 minus 27. 0. I like it. And then let's see. Let's try to plot it, see if I need more help. So negative 4, negative 5. So I can do this if you want to. Look at the paper, Jeff. There you go, my friend. Negative 4, negative 5. 0, negative 3. Negative 2, negative 1. It looks like I don't need any help. So what I mean, if the points are like bouncing like crazy and you're not sure how they're connecting, then you need more resolution. Then you need more points. Let's see, where am I? Negative 4, 1. And then 0, 3. Does that look anything to anybody?
Looks
Yes.
like a sine wave.
Yeah, it's interesting. It does look like a sine wave a bit.
Sideways.
Sideways, yes. But we know it isn't. So what could a cubic look like? Doesn't a cubic look like this? Could it also look like this? Could it have a bit of a... So what we're seeing right there is the middle part of it, this part.
Sleek like an Egyptian.
Okay. So when I do you all agree that a cubic could look like this?
Mhm.
Yes, because we know it has at most 2 turning points. So do you see how the middle part looks sort of sine-like?
Mhm.
That middle part is what we're seeing here.
But from a Y perspective.
Yes, exactly. So if I did like this, now it looks more like just a cube.
So parametric equations from a Y perspective.
Say again?
Parametric equations from a Y perspective.
No,
Not-
no, definitely not.
not
No.
all.
Okay. Just depends on, if I turn these around, then this would have done like this. It would have been like what you would say from the X perspective. You see, so it depends on which is what. The Y is very simple. It's just a linear. Okay. But if I turn them around, this would have turned over. So now watch this. Everybody, go ahead and put this in here. I want to show you something really cool. This is a quick way to make a table of values. So if I have t cubed minus 3t squared, and I have 2t minus 3. You guys remember the good old table? If you go to table now, you should have txy. And sure enough, look. You can even go further if you need to. Do you guys understand what I'm saying? Now, just to remind you guys, is everybody getting this? If you're trying to play along, if you hit second window to table set, you can change this if you want to go by half a step. Now it's going to go by half a step. You could also change it to ask, so it's going to wait for you to plug stuff in. So you can make a very focused table, right? You all with me? Okay. Just so you know, that's a really good way to do this, but this problem could be on the part of the final where I don't let you use a calculator. So you have to be able to do it
Gosh.
both ways.
Can't you just let us use a calculator the whole way through?
No.
It's worth a shot.
Or your calculator passes the course, it goes on to have a nice life. You're taking this thing. It's not good.
So, it's the worst thing you could have said was no.
Oh, okay. Yep, exactly. And then how do I eliminate the parameter? I want to kill the t. What would I do?
You plug in the T into the
T from where?
from Y.
Good, so you take the Y one. Why the Y one?
Because it's simpler.
Beautiful, it's simpler. I don't want to try to solve this sucker for T. That would suck. I'm not even sure I could. But it would be really bad. It would look totally disgusting. So instead I'm going to solve it here. So I add 3 divided by 2. Now this whole damn thing I could throw in here. Dear God, don't foil that shit out and stuff. Don't worry about that. Yes, just... So Phil, this is kind of like what you're talking about. This is Y as an input. So that's kind of like why it's from a Y perspective. Is because the Y ends up as an input. If I turn these around, this would be Y equals X stuff.
Yeah.
Okay, good. Now, can you guys take a moment and do this? If you need a calculator, I still have them up here. Plot this in your calculator. X equals all this business, Y equals that. Catch up to you. Jeff, you can do it, buddy. Can you? Sign.
Ooh, it's an ellipse. Looks like a skateboard.
Oops. I didn't give us a range on the T, but normally, well, let's see if you guys are with me on this. If I make T go from, let's just make it go from -2 pi to 2 pi. That should cover everything. It's probably going to over cover it. Because the period of the functions in this problem are pi. So it's probably going to retrace itself. And my scale is actually not that bad. So now it's retracing itself. So yeah, that looks like an ellipse that has been shifted over, shifted diagonally. That is a really difficult thing to do in rectangular coordinates, but it's relatively easy to do in polar. What's up? Oh, neat.
Should we be in? Oh,
Yeah. Oh, of course. Now you guys, your calculator probably graphed it a lot faster because I still have mine on crazy resolution. So if I made this point, you could do it, Jeff. What have you done? What have you done? 0.5 or something. That should be plenty. Oh my God! No, maybe not. Sorry. 0.01. Let's see if that's better. Okay, that's a little better. Sorry. If you turn the resolution down too much, it'll go crazy. Because then it's so if I'm gonna turn a corner, but I only plot a few points and I connect it with straight lines, it's gonna look crazy. So if you want to really get that turn, you got to plot a lot more points to get that. Yeah. Okay. And then real quick, just the first thing I would do if I were one of you is I would say, okay, this is boring. They're all the same angle. Let's make them all different angles and see what that does to this.
I was making us plot that.
Look at that.
Yeah, if you make us plot that, we're done.
By hand?
It's like something from Star Trek.
Yeah, it did. It does. You're right. Totally. That's what I was thinking when I was doing it. Did anybody expect that?
No.
And all I did was I made the angles different. What if I make them all even? Oh, there you go. That is tripadelic.
So I'm noticing some of the lines are a bit thicker.
It's retracing, yeah.
Okay.
Because I gave it a lot of room to work with. It's still going. Oh, no, there it is. I let it go from negative 2 pi to 2 pi.
Okay.
If I let it go from 0 to pi, let's see if that's enough. See if it stops short. It should be enough. Yeah, there you go. And so I gave it a lot more, so it just kept retracing itself.
Okay.
Like, okay. All right, anyway, maybe some of you guys will just play around with that a little bit. Cool. So, the thing I want to talk about now, let's see, yeah. I want to talk, that is section 10, 5, 10, no, yeah, 10, 6, 10, 7. Let me make sure I know where I am here. 10, here we go. Okay, you can do it, Jeff. 10, 6, 10, 7, yes. Parametric equations graphs.
You're not gonna have a test on them?
What do you mean? Of
Yeah,
course.
that's Thursday.
Yeah, we have a test coming, yes. Let me do this. It's almost like we're in a 6-unit class or something. It's crazy. Who knew? Just remind you guys, if you didn't see this before, I made 10.5 stop at 33. If you already did 10.5 homework and you went further, great. You get to experience more. We have test 6 coming up, of course, on the 9th, which is,
Thursday.
yeah, so tomorrow I'll have the practice test. Wednesday will be review day. Yeah, I'm sorry I've only got 6 tests for you, but so in general, just to let you know, math people, we try to keep the number of tests equal to the number of units. So 176 is a 6-unit class, 6 tests, makes sense. If I was teaching a 2-day-a-week 176, I would have given less tests. Just they would have covered more, because then we would have been meeting 3 hours a day. So thankfully we're not doing that. 3 days a week is perfect for 176. 4 days a week, there's just not enough time. Okay. So that's what we're doing. We're trying to make enough time.
There's more time in 3 days and less time in 4 days?
Totally. Yes, because you meet longer
Oh.
3 days a week. So there's time for me to do a concept, do some concrete stuff, introduce the next day. Yeah.
What about the summer?
Summer kicks ass because there's plenty of time. It's awesome. I love it.
It's just 3.5 hours a day.
Yeah, buddy. Yeah. But the nice thing is you're done in 6 weeks. So, right? So you're like paying more on your loan, so you're done with it quicker. Okay. So I want to talk just a little bit about section 10.8. Vectors. So let me ask you this. So speed, you all know what speed is, not the drug, I mean as you're moving in your car, speed. What's velocity?
Speed with the direction.
Good, I love it. The difference between speed and velocity is velocity takes into account the direction that it's headed, right? So if Jacob and I are both going 50 mile an hour, but he's going east, I'm going north, our speeds are the same, our velocities are different. So velocity includes direction, right? So velocity can be negative. Velocity can be negative because if I'm talking about direction, if I'm going north, I could consider that positive, so going south would be negative. You guys all agree? Speed doesn't give a shit. Speed is just the raw number that defines how quickly I'm moving. It doesn't care what direction I'm going. What about the wind strength? How much the wind is blowing? When you hear about the wind, do they give a direction also?
Headwind or tailwind?
Sure, totally. So if you're in a plane, it matters which way the wind is blowing, because you could take longer. So if you go from the west coast to the east versus east to west, the Gulf Stream messes with you sometimes. So one way might take longer than the other. Are you guys kind of with me? If anybody's flown, you know this phenomenon. Also, time zones make it all interesting. But
Oh,
yeah,
I know.
yeah. Jet lag is a thing.
just like fly halfway across the world.
Yeah, totally. So, the idea of vector. So wind is a really good one. Let me show you this. Let me find it and I'll show you. Well, let's just do this together.
There's also wind shear. Well, that's another thing.
Okay, let me see. Oh shit, let me just go here. Oh,
So we have 2.5 weeks left.
say again?
Mm-hmm.
So we have two this week, next week, and then until Tuesday left, correct?
Say it one more time, sorry.
We have this week.
What's the
we have
last day
next-
of class?
Last day of class would be, so we have this week, next week, and then till the next Tuesday. Not Tuesday, upcoming Tuesday.
Sure, yeah, whatever. Again, it's all on the homework sheet, so I don't have to keep my head. So you all know what's going to happen. This is a plot of the wind currently in San Diego. It's not a great example because, how do I zoom back out? Oh, temporarily offline. Well, that's good. Let me see if I can get a better one. Well, this is okay. Yeah, this is good. Do you guys see how some of these are smaller or not as long as others? So the length of the line represents the strength of the wind. So there's really strong winds, it looks like down here. These are really long. You can make them happen again there. These are pretty long compared to there. Bakersfield, not getting very strong wind right now. Out in the ocean, pretty damn strong wind. Are you guys with me? So the length of this line tells me how strong it is, and the direction the line is going is obviously the direction that whatever it is going, in this case the wind. So these things, these objects, are called vectors. A vector has a magnitude, which is like the strength of the wind. It's like the speed of the car. And a direction. So a very simple example, not about speed of car, strength of wind. Let's talk about moving.
Wait, can you go up real quick?
Sure. So if I have this box sitting on the ground and I want to move it, let's just do an aerial view. So we're looking down on this box and I'm going to pull it this way and somebody else is going to pull it that way. Which way will it end up moving?
That way.
Depends on how strong each of these are, to be honest. If this person's stronger, it's going to move more in that direction, yes? If they're equally strong, and this is let's just say 10 units of strength, it's actually newtons, but I don't want to make it fully physics. Then it's going to go right down the middle. That'll be the resultant. So this would be the resultant force. And this is shit we know. We know this is true. I know if I pull this way and you pull that way, it's going to just move forward. We're sort of, why is that true? Aren't I pulling it diagonally? But so are you on the other side. We're both pulling it diagonally. So let me see if I can get you guys to be with there. So look at this one by itself. Isn't there a component to the west and a component to the north? So we'll call this force 1. Isn't there a x component and a y component? Isn't there the same thing for this one?
Yeah.
There's an x component and a y component. What are the x components doing to each other? If we're assuming these angles are the same, for example.
They're opposing.
Are they working together or working against each other?
Well, kind of both.
The x pieces.
Oh, the X, they're opposing.
They're working against each other, exactly.
Yes.
So if I pull a crate diagonally and nobody else is doing shit, it's going to come right at me. But if somebody else is on the other corner pulling diagonally that way, the part of our force that's going sideways is going to cancel out. So the box is going to end up moving straight. Even though I'm pulling this way, they're moving that way, it's going to end up moving straight. We all know this from experience in the real world. What did I just create when I drew this? Is everybody with me on what I drew there? I just took each vector by itself and broke it down to parts. There's an x part and a y part. So didn't I just make 2 right triangles? Doesn't trig come into play then? Yay! So there's one thing. So I could take, this would be, let's see if you guys are cool with this. This would be negative 10 cosine theta. This would be 10 sine theta. This would be 10 cosine theta. And this would be 10 sine theta. So these two cancel each other out. And these two add to each other. So we will end up pulling it this way with stronger force, but the 2 parts that we're trying to move it sideways cancel out. That's why it ends up going forward.
Is that supposed to be negative 10 cosine theta?
Totally, right here? Yeah, because it's going back. So if I define this way to be positive and this way to be negative, that's the vector part of this. That's the negative sign, meaning it's just going backwards. So that's the immediate use of vectors. I can have a bunch of different forces acting on an object, and I can kind of figure out what's the result of all of them. If I break each one of them down into an x part and a y part, I can add all that shit together and see what the result's going to be. Which way is this thing going to move? All right. Let me take it down one more step. So fundamentally, all that a vector does is it points at some position. So let's say this is x, this is y. What's the magnitude of the vector? All the magnitude means is the length of it. How would you figure out how long that vector is? You all know.
A tangent.
No! I don't give a shit about the angle. I just want to know how long it is.
Sine.
No.
Just X.
I haven't told you shit about an angle.
Just X.
It's a right triangle. How many sides do we know?
30 or 2, sorry.
We know 2 of them.
Squared,
How many?
X squared. That y
Yes.
squared makes r squared.
Totally. Okay. So let's call this vector u. So vectors have a little symbol on top that tell you they're a vector. So the little symbol on top looks like part of an arrow, right? So instead of drawing the whole arrow, we just kind of do that. That means that's the vector u. I can have another vector and I can call it vector v, for example. So it's just names like x and y. The magnitude of the vector, here's a symbol that we know. And let me ask you this real quick. A little side note. If the point was 4, how long is this vector? 4. Thank you. If the point was -4, that is pointing at, how long is that vector?
4, -4.
How long is it?
4.
4. Isn't that the absolute value?
Yeah.
So it's not surprising then that in general, the form, the notation we use for the length of a vector looks like the absolute value, because that's what it really is. This notation is more than just absolute value. It's the length of a vector. It's just if I'm talking about one dimension, it's easy. So the length of this vector would be the square root of x squared plus y squared. That's r squared equals x squared plus y squared, and then I take a square root. Okay. So let me say this. I think you guys are going to perk up at this. Section 10.8, extra credit. Next class, I have to focus on 11.2, which is systems of equations. Vectors are important, but it depends on where you're going after this. Vectors are built right off of trig. It's right off of it, just another use of it. It's not that hard to pick up once you understand trig. We need to talk about systems of equations and work our way towards matrices. We got to get to using matrices to do stuff. All right, so tomorrow I'll have the practice test for you guys. We'll get into chapter 11. Okay.
Chapter 11,
There it is.
Oh, thanks.
Thanks, man.